So without further ado, I guess we can start with the first part. This first half is going to be about Subriemannian geometry itself. And before telling you what I'm going to talk about, keep in mind that Subriemannian geometry is one of many names for the same thing. Gromov in 1981 called it Carnot-Carré-Théodory geometry, and there are very good reasons for that. So the metrics that we will see, they appeared in a more general form in the beginning of the, what I think 1909, 1910 or thereabouts, in a work from Carré-Théodory on thermodynamics. And so that's where the name came from. And in fact, what we will call admissible horizontal curves are adiabatic processes in terms of thermodynamics. And the proof of the existence of these curves were done in terms of Carnot cycles. So Carnot didn't really do much on that specifically, but in the context of thermodynamics, you have Carnot cycles appearing, and this gave somewhat the name to that geometry. If you look at other literature, they are also called singular Riemannian geometry, and the book by Brocket of 1981 is actually very nice on the subject. Different name, same exact thing. I learned Subriemannian geometry the first time from the paper by Strikarts that is beautifully written and equals them Subriemannian geometry there. I don't know if that's the first time they're called like that. If you look at the Russian school, there is a lot of literature of non-holonomic geometry. Again, this is exactly the same thing. And if you look at Hermander's work and the theories of sub-elliptic geometry, hypoelliptic operators, again, you go back and do the same kind of stuff. So this is the limited amount of name that I'm aware of. But the topic's relatively young, but it has been treated from very different point of view. And so you might incur in names or might be familiar with names, with different names, and then realize that the subject is the same. So this is a long parenthesis, but I just wanted to make that clear and warn you. So if you're reading something and it looks familiar, it might really be familiar. I'm sorry. Sometimes I try to change the slides using the keyboard and then nothing moves. So this is part of the recommended readings that I'm going to put that you can access. So I won't talk about that. Lots of these things are legally freely available online. So I guess on this slide, besides the book by Montgomery, you can legally download all of them from the respective sites of websites of the authors. So it's not even that expensive to start learning about the subject. And the video courses on the end, they are, okay, they were registered at a time where people were starting registering the courses in 2014, so they are recordings of blackboards. It's not as good as recording talks with a microphone and shared boards like on Zoom, but they are very nice and they cover even more subjects, again, than what we're talking about, including a lot of optimal control, optimal minimal surfaces, and stochastic processes. Those I won't read at all. So let's start finally. This was long introduction on namings and resources. Let's start from an example. So I want to start with the foundation of the city of Carthago and use that to construct one of the most famous examples of Subriemannian geometry and use that as a prototype for all the rest of the first part. The rest of the talk will be about formalizing what we see in this simple example and start looking in what's wrong, what are difficult things, what are interesting things, what kind of construction do we need, and so on. But for now, it's still all very vague. Let me ask you something. If I do this, can you see the red line? Perfect, thanks. So let's start with some mythology. Dido was at least mythological characters. I think it's not clear if she existed or not, but she lived in Tyre in Lebanon, and she was the sister of Pygmalion, that was at a certain point became the king. They were the son and daughter of the king at the time. And at a certain point, for a reason, she decides to live with lots of gold. And what happens? She arrives on the coast of Tunisia and asks the king there if she could buy a piece of land to settle. And the king thought of being smart and say, okay, you just take the bull side, whatever you can enclose using that, that's yours. So what happened is that Dido took the bull side, made a long, thin strip with it, and then encircled the land on the coastline of Tunisia. And it turned out that that land was really a lot, or at least it was enough to found a new city. This is how Carthago was born. And so the problem of finding the curve that optimized the area in that case was solved a long time ago, but this mathematical formalization had to wait a few thousand years. And so this is what we're going to do now. Let's try to give, let's try to put some mathematics into the problem. So the king of North Africa granted a request to take as much as coastline land as she could. So we have a coastline. We have this is, let's assume that it's straight for simplicity. We have a fixed piece of land that is our coastline where we can start trying to encircle the land. And then we have to enclose this land. So we're talking about some area using some rope. In this case, a rope made of thin strips of bull hide. So we have our coastline. We have a rope that is touching the coastline at 2 fixed points. And now we want to move this rope so that we can get as much land as we can. And so let's give name to these things. Let's call omega whatever shape is enclosed by the land line and the curve. Let's call gamma of t this curve so that we can imagine walking along the curve and describe it as we walk along. And let's try to see how we compute the length of a curve and how we compute the area of some Euclidean piece of land. So this should be familiar for everybody. I try to keep it as simple as possible. This, if you have done a bit of curves and surfaces or a bit of Riemannian geometry, then you know that the length of a curve is just the integral of the square root in the Euclidean space of the derivatives of the two components, x and y. So here we are in the plane, say x and y. Please rest. Okay, it stays there for a while. And the area is just the integral over this surface omega of the surface omega dx dy over this shape. We want to keep this thing here fixed, but we want to move gamma so that we find okay, what we want to do is we want to fix gamma and then we want to move it around so that omega is the biggest. An alternative way of doing that, and this is what I've written here, is that instead of maximizing the area by fixing the curve length, we can say, okay, I know how much land I want to, but what is the shortest curve that can give me that length? Then it's basically the same problem, but you are flipping around what you're maximizing or minimizing. Is that clear? So let's do that. Let's think of the problem in the other way around. We fix an area and we want to find what is the shortest curve that can give us that area. Then we do some computation. If you have the x wedge y, what you can do, you can say, yes, I can get there by taking 1/2 of d of x dy minus y dx. So I'm putting here one forms randomly. And then you say, oh, but there is Stokes' theorem. I can remove these from one place and take boundaries from another place. So I can take here the omega, and I would get my curve plus the piece of land. Here I'm cheating a bit. And I would rephrase my integral in terms of this other formula. So I would have a of omega is equal to this integral. Why would we want to do that? For once, we moved from considering both big omega and small gamma to just having small gamma appearing in all the formulas. So at least we simplified a bit the problem. But yet it's still not enough. It's not flexible enough yet. So what we can think of is making this area an additional variable. And then we can think of lifting our curve from the plane to a curve in three-dimensional space in which the third coordinate keeps track of the area we are enclosing. And that's what is happening here. So we have a third coordinate z of t that keeps track of the area that is being enclosed. And now we start getting there. At least we can formalize a bit better the problem. Since z, because of the computation that we have done, was equal to this integral, when we look at this curve gamma and we look at what constraint do we have for this curve gamma, when we take the derivative with respect to z, essentially what we see is that there is a special constraint of z. Z will have to satisfy this differential equation that involves z dot. So when you have this kind of constraints that involve derivative, this is what is called a non-holonomic constraint. And this is something that relates back to the names I was telling you at the beginning, that in the Russian school of non-holonomic mechanics, they were studying Subriemannian geometry. We will get there soon. Studying mechanics with constraints that involve velocities is essentially studying this kind of non-holonomic problems. And another way to write this is we have this one form, dz minus 1/2 x dy minus y dx. Where did I get this? You get it straight from here if you take a d of this z. Practically, if you move z on the other side, you will get that dz minus 1/2 x dy minus y dx has to be 0 for our curve. And this is what I'm writing here. When you apply it to the vector field, for the vectors that describe the velocity of our curve, you're saying that our curve must be in the kernel of this one form. And now I'm starting introducing the language that I want, because the fact that this curve lives in the kernel, the velocities that allow this curve to evolve, live in the kernel of this one form, is the way we describe what are admissible curves. What curves can we accept as possible curve that will minimize the area? And this is what gives us the constraint. And so the full Dido problem can be rewritten by saying, I want to lift my curve gamma into a curve in the three-dimensional space, but that keeps track of the area, and that satisfies this non-holonomic constraint. It lives in the kernel of a special one form. And the problem becomes, find this curve in the three-dimensional space that satisfies the constraint, that gives me the area that I want. This Z1 is a fixed endpoint with the area that I want and with the endpoints of the cost line. So this is the X for the L cost line, this is the Y for the L cost line, and this is the area. And then you want that the length of this curve is minimal. But now this is here where things get a bit weird. This length is the length of little gamma. So what we are saying is that we want to minimize this problem by redefining the length from the curve, not as the general Euclidean length in 3D, but as a length that keeps track of the original problem we have. As this length will take only an interest on the X and Y, on the plane over which we have lifted it. And this constraint here is the one that will deal with the third coordinate Z. And the fact that here we are losing a part of the space is something that is going to create problems. But by reformulating the Dido problem in this way, we have basically put on the screen all the ingredients that we need to define the sub-Riemannian geometry. And this is, we need an ambient space. So in this case, it's R3. Our points, our curve will live in R3. We need some subspace of the tangent space. So some subspace of the directions in which you can move that is structured enough. And we will make sense of structured enough later on. And we need a notion of length that plays well with the structure. So you see, the constraint here was a constraint on our curve on the XY plane, and we really did care only about the curve on the XY plane. And in some sense, this length here is made in such a way that you keep having interest only in those XYs. Yeah, I'm cheating a little bit, but this is essentially what is going on here. We are restricting a length only on this subspace of curves we are interested in. And this subspace is no longer three-dimensional, it's two-dimensional. And so let's actually go and give a brute definition of this. Before I move on, is there anything unclear here? Especially if there are master students around and something is not clear, please yell. So I take this silence as either sleeping or everything is fine. So let's move on. So let's put this thing into Word. We want an ambient space. So I'm saying that we can get any smooth manifold and that can work as an ambient space. If you have done a bit of mechanics, you know that you can define Lagrangian and Hamiltonian mechanics on manifold, and they define generalized coordinate on curved spaces. So you can imagine this is the same kind of thing. And then we want this D, a vector distribution. That means that there's a local assignment of subspaces of the tangent bundle that is regular enough, say it's smooth. So you change the point and you have a subspace of the tangent bundle defined at each point. It might be the whole tangent bundle, then you will have a Riemannian manifold. If it's a proper subspace, then it's the kind of more abstract spaces we are talking about. And then you want a Riemannian metric G, but you want this is essential, defined on this D, on this distribution. So you can measure products, but only on this subspace. Here, before moving on now, for whatever is not an expert, you can turn off the volume for a minute. But for experts, this is not the most general definition. So you can define this in terms of more general bundle. And I think, as far as I'm aware of, the most general definition is the sub-Finsler metric. And this is, sometimes they call it generalized sub-Riemannian manifolds. And so here, instead of having a Riemannian metric on D, you have a vector bundle over M with some norm that doesn't have to come from an inner product. And then you have a morphism of vector bundles that sends it into the tangent bundle. And then you use that to define the restriction of a metric by projecting this thing into the tangent bundle. If you look at the lecture notes by Enrico Ledonne, they are basically developing almost all the theory we're seeing today in terms of sub-Finsler manifold. And then, of course, lots of results will have to generalize to more simple structure. But just so you know, this is not the most general thing we can say. But it's the one that is, sorry?
Can I ask a question?
Yeah, sure.
So this D, is it a sub-vector bundle or is it just an assignment of subspaces?
It's enough that it's an assignment of subspaces. You will have to require something on it, but if it's a sub-vector bundle, it's nicer. Okay,
and G, is it a metric on D as a manifold, or is it like a Euclidean metric, like
No, it's a metric on D as a manifold, but you can take in particular the Euclidean one. In fact, what you can prove is that if you take a metric as a manifold and you take a general bundle there, they are always equivalent to what's called the free sub-Riemannian manifold, in which the bundle is just Euclidean. So you have a local trivialization of this, and you can take RK for that.
But so it's in particular, it's an inner product on all the fibers of D, or
yeah, point-wise.
Yeah, okay, yeah.
Is that? And so we have this. Oh, sorry, I was sliding, and then the gesture made YouTube appear here. Okay. So let's compare again. We have a smooth manifold. In the case of the Dido problem, we have R3. We had the vector distribution. In the case of the Dido problem, this was the kernel of that one form. And for people that do contact geometry, they already know what this structure is. And we had the extra thing that is a Riemannian metric on this D. And in this case, the metric was this dx squared plus dy squared was the square root of x dot square plus y dot square when you compute the length. Look at it in the way you prefer. But it's this diagonal metric that only take into account x and y in the case of the Dido problem. And then there we were looking at curves, and really apologies for changing notation. This little gamma now is the old big gamma. I've realized this only after I've written all the slides, and because I'm writing them, it meant an insane amount of work and redrawing lots of stuff. So in the end, I decided, no, I'll keep it this, otherwise it takes 2 days just to change that part. So apologies, this is our old big gamma. And we have these admissible curves. They were the curve whose velocities were living inside the distribution. So whose velocities were in the kernel of the one form. And then we have our length, that is the length with respect of this Riemannian geometry on D. And now you see why you want the metric that is adapted to the distribution, because point-wise, you want to make sure that you can compute this inner products of gamma dots. So these gamma dots must live in the space where G is defined. And this curve that I've called admissible, they are usually called horizontal curves. And those are where the adiabatic processes that I mentioned before. And what you do usually to work with this is take a more convenient point of view, and this relates with that thing that is sub-Riemannian structure are always equivalent to this free sub-Riemannian structure. You can always locally find an orthonormal basis of vector field that spans your distribution. And so what you generally do is, well, if you have it global, then that's just amazing. But otherwise, just say I have a local one. This means that for all Q in M, this Q is the span of the vector fields x1 at Q, blah, 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 xk at Q. And this gives you your subspace. And because of that, it can be that this thing changes dimension when you change the point. So it can be that you have k is equal to 3, and then suddenly is equal to 2, and then suddenly is equal to 5. So the dimension of this this vector distribution can change point-wise. So this is something that one has to keep in mind. And it's called the rank of the distribution. So what would be one possible base for the case of the Dido problem? Well, one of them, and I'm writing that because I'm going to need it soon, could be take the first vector field to be dx minus 1/2 y dz, and take the second vector field to be dy plus 1/2 x dz. And if you write down a generic vector with those x1 and x2, you will see that z3 will get a formula of the form dz minus 1/2 y then dz plus 1/2 x then dz, and will recover somewhat this extra requirement that a curve in the distribution has to be a curve that kills this one form dz minus 1/2 x dy plus 1/2 y dx. And do the computation, try to do it. If you have issues with it during the question time, I'll do the computation for you and I can show you how it works. But so how do we know that all this stuff I'm saying is not just made up on air and it makes sense? And how do we know that we can actually find those minimizers? I mean, our problem, original problem, was to find a curve that minimized this special distance on somewhat constrained subspace. And so the rest of this part will be trying to see how these things makes any sense. So what does it mean to be admissible? If instead of writing the formula as I did before, I want to draw it, means that at each point Oh, I'm writing on it, sorry. At each point, I have a subspace. This is embedded in R3. So in principle here, I should have a three-dimensional space of possible directions. Instead, my curve can have a velocity that is constrained to this little green square. And so it says it moves in this direction and it keeps going. And at each point, my velocity has to be constrained on this subspace of the full space. And so you see, in this case, the curve can move around in space, but imagine that our distribution was flat and was in the XY direction all the time. Then we had no way of going up. And so we had no way of reaching that area that we would like to reach in the case of the Dido problem. And here is a crucial point. If you take the product of this x1, x2, so if you take their commutator, what happens is that you don't remain in the same subspace. X1 and X2 live in D. So this thing is in D, this thing is in D. They are embedded in the tangent space. Once you take their commutator, what happens is that you live. So this is really the crucial property. X1 and ADZ and X2 and ADZ live in different spaces, and yet there is an operation you can take on the space that allows you to live. And if you look at this picture, actually, this one down here is the wrong picture, but they were so nicely similar from Wikipedia that I took those. If you look at this picture, you see that here the planes are flat. So if you move in the direction of the line I'm drawing, you can't escape. You are stuck on this plane. You're in a similar situation of what you did see on the right. So if your commutators were remaining inside the same space, it means that you are foliating the space with invariant manifolds. And it means that you are constrained to remain inside a place that can't be left. If you need to join a point that was here and a point that was here, you can't cross across these layers. You're stuck on one layer. But if things are curved enough, and in this case, you have this rotational part, then it means that if you move slightly on the side, your planes are becoming transversal. And so if you move slightly on the side, your velocity allows to go a little bit high. And if you move slightly on the side, you go a little bit high as well. And in fact, if you look at the real picture of the vector fields that we have here, you don't see this. You would see essentially a circle. And then you would see that on the rays of this, on the rays, you have planes that starts bending. So you have a rotation on the rays and you have a rotation around this circle, this axis. We'll come back to that thing. And there is actually a nice picture. I have it written down somewhere. There is a guy that wonderful pictures for this online.
Patrick Masson?
Yes, thanks. Patrick Masson. So if you look for standard construction and Patrick Masson, and for me is Massot, M-A-S-S-O-T, then on his website there are beautiful pictures, and one of them is exactly with this circle and with this plane that rotate. And this is exactly the structure that we have here on this formula. I'm going to show you what is the equation for this one later on, but just so you know that here I've been cheating a bit. But this is essential. The fact that things are bending and you can escape. And in fact, the way you write this property here is that if you span x1, x2, and their product, their commutator, then you have covered the whole tangent space. So morally, you can go in any direction. And this is where we're going next. And this is where lots of the names, again, are coming back. So there is a condition that you always require on sub-Riemannian geometry. It's called Ormander condition. It's called bracket generating condition. It's called being completely non-integrable or non-holonomic. There are plenty of names for these things. But essentially what you're saying is, if I take enough Lie brackets of the vector fields, then I will span the whole tangent space at each point. And so I will be able to escape and go in any direction. I just have to try enough. And the minimal number of commutator that I need to take so that I span the whole tangent space is what's called the step of the distribution. So if later on I'm talking about a step 2 distribution, that's what you have just seen. I need to take my space plus one commutator. So 1 plus 1 is step 2. If I need to take an extra commutator, so if I add x1 x2, x1, for example, and I needed also that would have been step 3. If you want, you can count how many things are inside these Lie brackets to have an idea. And why is it useful to have this bracket generating or Riemann condition assumption? Is because under this assumption, there is this theorem by Cho and Rachesky. Sometimes it's just Cho theorem. That's a bit unfair because Rachesky did find it before. But there is this theorem that tells you that if your distribution is bracket generating, around each point, you will find a neighborhood, might be small, but you will find a neighborhood such that every 2 points in the neighborhood are connected by an admissible curve. So what this thing is telling us is that Dido could find that minimizer for the, well, Dido could find a curve that reached the area that she wanted. And she could find it because the distribution in that case, this one here, is bracket generating of step 2. And so we are guaranteed that we can always find a curve that connects 2 points. Why I'm saying we can always find a curve is that because we can patch the space. So if our 2 points are far enough, if I take enough neighborhood that connect them, unless our space is really, really horrible for other topological reasons, then we can connect those 2 points. But before going back, I will show you what is the idea of the proof, but I've basically already told you what is the idea of the proof. Let's see as a more down-to-earth example. Let's think about a unicycle, or let's think about parking a car. So if you replace this with a bicycle or with a nice little box with electric or a fuel engine, maybe fuel engine is better given that we have Carnot groups and all this thermodynamics involved. But anyway, if there you put something that moves around with wheels, then you are in some kind of the same situation. You have something that has a direction, it can move forward or backward, and that has wheels, it can turn the wheels. So the unicycle is the simplest to draw, so because once you know that you are in this 3-dimensional space of being somewhere on the ground and pointing in some direction, then how you move forward or backward, then you move in this direction that is the projection of the vectors x, y in the direction you have. And how you steer, you just change the angle. But you know that if you try enough, you can park your car almost everywhere. And what does that mean? That means that if you turn your wheel and move forward, and then turn your wheels and move backward, and then turn your wheel, move forward, and so on and so forth, you will finally park your car or your bike somewhere. And that's because by turning the wheel and moving backward and forward, you can go basically in any planar direction. You need to do it with a few maneuvers instead of just saying, I just go in that direction straight and translate there. And indeed, if you take the commutator of this 2-vector field, what you see that you move in the orthogonal direction. You will move in this direction. But you need to turn your wheel and move backward, and then you will be in that direction. That's like when you park the car going in rear move. And if you look, I think on Wikipedia, I'm not sure it's on Wikipedia, you need to check, but on some website, you will find the car example, and it's almost identical to this. And the bicycle example is the same. There is a beautiful paper by, I think it's Tabachnikov and Levy, that is about the bicycle track problem and how it's used to solve some conjecture. This kind of geometry that is involved is the same. And this is also a case of contact geometry, by the way. And so we are, again, this is an example of step 2, sub-Riemannian manifold. The manifold now is not R3, it's R2 times S1. And the constraint is essentially living on the span of XY, on the span of these 2 vector fields. And it's bracket generating. So this guarantees that we can go everywhere with the bike. This is very important in the Netherlands. So let's go back to Rachesky. I think I've made you an ad like this about this. You can go everywhere, you just have to try enough. And that's essentially the proof of the Rachesky theorem. It's a bit more technical than that, but the moral of the story is that one. You can achieve the non-horizontal direction by steering and going backward and forward enough. And so when you look at, when you move in one direction and then move in the other direction, and then you move back from that direction, and then, well, I'm doing it the other way around, but you move here and then here and then here and then here. What you're doing, you start from a point, you're evolving on that vector field, and then you start another point, you're evolving again, and then you go backward, and then you go backward, and look, you have not arrived at the same point. You have not closed the loop. You're not in an integrable foliation here. You're not stuck to that plane. You have jumped. You're doing it slower. Here, imagine that t is very small, so you're in a little neighborhood of your point. That's why you have this neighborhood in some sense. You want this expansion, and this expansion holds for small t's in principle. You want this to be a small error. So this t is little, t squared is even littler. You're going very slow. And if you need more commutator, you're going even slower. But you will get there eventually. So once you have this, you're done, because then you can show that by moving enough, you can connect any 2 points, provided that t is small enough. And that's essentially the key idea in the proof. There are alternative proofs. And if you take the literature that I've given you, I think you find 3 or 4 alternative proofs that use idea from control theory, that use idea for geometry, that use more abstract means. But I think this is what I find the clearest one, because it gives you like this splatter the key in your face. It's just this non-integrability that plays a big role, the fact that you can escape your distribution. And so once we know that we have this curve joining 2 points that are close by, if we patch enough the space with bolts, we can join points that are far away. And then we can use this to define the distance. Here I'm going to call it Subriemannian distance. Some papers do, but most papers call this Carnot-Carothèodori distance, and from Gromov names. But this is just the infimum over all possible admissible curves joining 2 points. So you might have different ways of patching the space here, and you might take different detours here and there and blah, blah, blah. But you take the one that gives you the shortened length with respect to that Subriemannian metric that we had laying there since a while. And this defines a distance. And thanks to Choroszewski, you can prove that this distance exists. The weird thing is that this distance is nice, but not that nice. Up there, you see an example that we are going to discuss in details later on. And what you see in this example is the wavefront of this distance. So you start from a point here from 0, and here you from somewhere on the right of 0. And then you start evolve, and then you go on the points that are at a fixed distance from there. So you look at a sort of a ball, and you find that this ball has a very weird shape. It looks like, in this case, it looks like a butterfly, but we will see that it can be worse. And I'm going to come back to that, but it's not nice, this distance, and yet this you can prove that is continuous, that is finite. So if 2 points are there connected, they will have a finite distance, and that the metric space MDSR will come with the same topology as the manifold M that you use at the base. So this thing will not destroy the structure that you have there. And this whole thing, these are basically immediate consequences of the Choroszewski's theorem and the proof that you will have for that theorem. So it will lead to weird stuff, but it's not that bad of a distance. And so we have found a metric on our space as a metric space now that is induced by the Subriemannian, the geometry that we have put there. So let's look at our example. Let's look at our Dido problem. This Dido problem, that is a Subriemannian structure of on a contact manifold, is what's commonly called the Heisenberg group H3. And I'm going to say something about that later. The ambient spaces are 3. This is the span of the distribution that we used before. These are the vector field that gives you this distribution that I was showing in the old picture. So it's just, you have something called a normal form, some canonical coordinates, and usually you tend to work in canonical coordinates. And if you take those canonical coordinates, you will find this. If you look at the unit sphere for this structure, this is the unit sphere. is like an apple that is squeezed in the middle. Here is 0. And it's made of spirals that spiral up, and all the length minimizing curves here are curves that when you project them down on the plane are circles. And these balls have some problem. When you put that metric that I was telling you, it's never smooth and don't even Lipschitz when the 2 points x and y are the same. So if the 2 points are aligned. So that's why you see this bad behavior here. And this is something kind of prototypical. It's a feature that you see often in balls. And then something that, yeah.
Can I ask a question? You're talking, you say length minimizing curves. You haven't shown that these are...
I've not arrived there yet, you're right.
Oh, okay.
But I was anticipating time, sorry. I will be there very soon. But even if you don't consider length minimizing curves, you just take all the points that are at distance 1, in this case it's a unit ball, a distance 1 from 0, then this is the thing you will get. And this is not nice at those 2 peaks. It's smooth in all the rest of the space, but here it's really bad. And before giving you better example, I need to add a little bit more on the picture. And now there will be a bit more technical slide after this one. So this is our distribution D. I'm making it pointwise here. I say that D0 is just 0. And then you have the flag of the distribution that is essentially a chain of spaces such that each space is contained in the next one, and it tends to on the wall tangent space. And each of these spaces is defined in terms of the previous space plus the commutators of the previous space with the distribution. So we take our distribution, we commute all the vector fields of the distribution with themselves, and we add them to the distribution, whatever it remains. And then we get our space D2. And then we take all the vectors that are here, take the commutator of those with the distribution, add back the space, and then we have the next space and so on. And we know that by doing this enough, we will cover the wall tangent space. And we note that either we have remained in the distribution or we have escaped and added a bit more direction. So this is the flag. This filtration is the flag of the distribution. The growth vector of the distribution is the dimension of all those spaces. So in the case of Dido, this is the actual distribution. It was 2, and then the next one was the actual tangent space, so was 3. So the growth vector was 2 and 3. And in that case, the growth vector did not depend on the point. So it was 2, 3, no matter where we were. So in that case, the distribution and the Subriemannian manifold that corresponds to it are called equiregular. It means that the growth vector is the same everywhere in the space. The dimension of those subspaces is the same. Oh, and here there is the Dido example that I was telling you about. Not all distributions are equiregular. We will see examples of that. One thing I wanted to add on that is that this is in general no graduation. So there is not a nice a nice structure of Lie algebra on top of it, but it's well defined as graded vector space. So it's well defined as a vector space in which you have your distribution and then the quotient of the next space with the distribution, and then the quotient of the previous space with the next, and so on and so forth. So this is always well defined as a vector space, but is well defined as a Lie algebra only when this is equiregular. And the whole theory, when you read about Carnot group, is about studying this. Equiregular vector spaces in which you can nicely add a Lie algebra here that respects the grading. So when you take commutator of 2 different spaces, you jump in the space that has the right power. This is for people that know what I'm talking about. So if you don't know what I'm talking about, don't worry. We won't use that too much. We will need this for the rest, for the second part, but I want this for a few things that I'm going to say later. So you know that there is some structure, and you know that there can be more structure on that. And you know that in some cases there is even more structure. So take it at that. And going back to Dido being the Heisenberg group, again, for people that know what I'm talking about, if you take R3 and you define the product of 2 points like this, so you sum the first 2 coordinates, and then you have something that resembles our one form here at the 3rd coordinate, then this allows you to define a left invariant structure. that's a non-abelian Lie group on R3, and this thing is the Heisenberg group, and this thing is essentially tailored to the Subriemannian structure that we have seen before. So the Subriemannian metric is left invariant with respect to the action that comes from this thing. And this is what's called a step 2 Carnot group. It's just the Lie group that is associated to an equiregular distribution with its homogeneous stratified Lie algebra. At least that's the way it has been explained to me when I've studied this stuff. Why I wanted to put this in the picture, I wanted to tell you about this because we will talk about the growth vector later on. It will enter in many of the things we're going to discuss. And because when you have this nice structure of Lie algebra, of stratified Lie algebra, you can define a smooth system of privileged coordinates, so a sort of normal coordinates or canonical coordinates, call them the way you want. But there is a nice way to define certain coordinates. And what people tend to do is use those coordinates so that you don't get lost by having strange notation. In the case of Dido, it would be those two vector field here, the x and y, x, d, z. They are not always uniquely defined, but modulo relabeling the variables they are. And this is important because if this is not equiregular, it's not granted that you have even a continuous system of coordinates around the point in which the growth vector changes. So not having this structure makes the problem 100 times more complex. So let's look at some examples. The contact structure is what we have already seen. They are step 2 equiregular. There is something called quasi-contact structure. Again, nice step 2 equiregular, just that they have even instead of odd dimension. And I'm not talking about the topology or other problems that are behind this, just to show that there are some notable examples. There is something called the Grushin plane. This is also spatial, but let's fix about the Grushin plane. In 2D, we span the distribution spanned by, we have M with the distribution spanned by dx and x dy. And here you see a non-equiregular distribution. When x is 0, you lose this direction. So when x is 0, this distribution has dimension 1. And so this is our first example of non-equiregular. I put Engel just for Alvaro. And I want to show you another one that I have no idea if it has a special name. I have copied it when I was at a seminar. I didn't write down a name and I couldn't find it anywhere else, but it's not something complicated to come up with. If you span a three-dimensional space, you take the distribution spanned by the x and the y plus xz dz. Then when z is 0, you will never be able to recover this. And so this is not Bracken generating. For z0, you won't recover the whole tangent space. So this is bad. This is not something we want. Another one that I'm going to talk about later is the Martinez structure. And this one is similar to the contact one, but you have y squared here. And the problem is that when you take the first commutator, you won't recover dz, you recover y half dz. So for what this thing remains span still the same two-dimensional space, and you need 3 commutators to get to dz. And the set y equals 0 as a singular set is a very special set. So I'll give you some example. You see that there is not just the structure that I was describing before. Let's come back to the balls. In fact, what I'm talking about is the spheres, the topological boundaries of balls of radius R. But one question that people had is, given that balls are so weird, and you see 3 different balls in the picture, if the radius is small enough, do they look like Euclidean balls? After all, the distance brings the same topology as the underlying manifolds. So it's a reasonable question to ask. You know that the topology is the same, maybe the topology of a small ball is the same as well. This is a big question. We don't know. We know it for step 2 and for Carnot group in general. But it's fully open. This is the first big question that comes in the slide. Baryshnikov paper is 7 pages. It's beautiful, clean, technical, but very clean. And that's the only thing we know, as far as I'm aware, about the topology of small balls. So we know that they are homomorphic to Euclidean ball, but only in that specific, those 2 specific cases. So we are almost at the end of the hour, and we are left with the last part. This last part is not very long, but I was expecting this first part to take longer because I wanted to go very slow on it. Are there questions on what we have said so far? Do you want to have a break now, or do you want to go on 10 minutes more and do this whole part, or take a break in the middle of it? Either thing is fine with me.
I think it makes sense, right, to wrap this up first and then make the break. Yeah.
So let's go to the geodesics. I mentioned length minimizing curve, and then I never went there. So let's try to define geodesics. We fix a sub-Riemannian manifold. We fix 2 points, and we try to find a length minimizing curve that joins those 2 points and that is admissible with respect to our sub-Riemannian structure. One equivalent way, modulo time reparametrization, but this is the same that happens in the Riemannian case, is that those gamma are minimizers of the energy functional. So instead of having the square root of x dot square plus y dot square, you have x dot square plus y dot square, morally. So we can look for minimizer of either this quantity or this quantity, but up to now, this seems like the same as in Riemannian geometry. And in Riemannian geometry, we know we have the Levi-Civita connection, the torsion-free connection that gives us a nice way of defining the geodesics. We have a nice Hamiltonian formulation in terms of the metric. We have the Euler-Lagrange equation that can tell us that there is a unique parameterization given an initial vector. So you give a point, initial speed, and this uniquely define your geodesics. So you have nice, beautiful structure. All these representations are equivalent. Unfortunately, this thing is lost. For once, and I won't say anything more about what I'm saying right now, except what I'm going to say, if you look for a torsion-free connection on a sub-Riemannian manifold, unless it's a Riemannian manifold, so D is the tangent space, the tangent bundle, and not a proper sub-bundle, unless you are in the Riemannian case, there is no torsion-free metric. There is no torsion-free connection. So you don't have this. This is out of the picture. There is another problem. If you think about the parameterization by initial speed, the initial speed lives in a smaller space. Let's say it's a 2-dimensional space and not 3-dimensional space. So dimension-wise, you don't have enough space to cover all the possible curves. So this won't work. We are left with trying to make sense of this, basically. And that's where we are going next. So we have lost the possibility to go and look directly at the tangent space because there is not enough space a priori. We don't have this special connection here. We might be able to see what happens if we lift everything to the cotangent space and then project on the manifold and then get the geodesics as the projection of a cogeodesic. May it work? I mean, if I'm saying it, it's because it is, but in principle, it doesn't have to. So now I'm taking a big assumption. I don't want to get into technicality, so I'm saying that D is the span of x1, xk. It's global, everything is nice, and k is smaller than the dimension of our manifold. So manifold is dimension M, distribution is dimension D. If you take your curve and you write what it means, that is directional, its derivatives live in the distribution, so that the tangent vectors are in the distribution, essentially you're saying that point-wise, your curve is a linear combination of vectors in the distribution. So what I'm saying here is that point-wise, for each t, this thing is a linear combination of vector in the distribution. If you go to the length of defining a generalized Subriemannian manifold and then showing that every Subriemannian manifold is equivalent to a free Subriemannian manifold, and then you can basically prove that this is always the case. I don't want, but I'm just saying that by looking at the fact that it has to live in D, it must be a linear combination of things in D. And then you say in a more technical way that there is a control, so a function from 0, 1 to Rk, so k function from 0, 1 to n, these ui's, such that gamma dot of D is some weight that change with time, and then your curve, the directional derivative of your curve in the direction xi. This is what this formula is telling you, essentially. There is a reason that we want this here to be L2 or L infinity. There are reasons that you want boundedness. I can give you a counter example later if you don't take bounded stuff, but I don't want to get into that rabbit hole right now. And then we know that this curve starts at a certain point x, and we are going to look for curves that end at a certain point y. Now we need a bit more technicalities. We look at the endpoint map. This is a map that takes one of those control u and tells you where the curve will end. The gamma that is associated to that control u will arrive at that point there. And so changing the control, if you start from x, changing the control, it might be that you go to a different point, like in this example, or it might be that you do a different detour, but you end up in the same point. So this map, there might be many u's that brings you, that connects to point. It's not hard to show that this is smooth and open. And then you define your constraint problem. You want to find an horizontal curve, so a curve that satisfies this differential equation with this initial condition, with the constraints that the endpoint is the y that you had prescribed, and that minimizes the energy functional. I repeat, you want to minimize the norm of this curve with respect to the Subriemannian metric so that your endpoint is going to be y. If this is orthonormal, and you can always do that locally, it means that when you take the scalar product with respect to G, you are just saving the U. So this is translated from gamma to just the norm of those U's. And now you see why you want the norm R2 to be defined. So we want to minimize the norm of these controls for the controls that brings us to Y. And so now we are just doing minimization. We do a variational problem on Banach spaces. We use Lagrange multipliers. I can tell you later during the question time, if you want more about Lagrange multipliers, I can tell you all the details, but essentially this is a way to encode the constraint in a variational problem. It's the same Lagrange multipliers you see when you do mechanics, but now it's on Banach spaces. And then we have a problem. So the Lagrange multipliers are fine when you are on regular values of Ex. So when the differential of this map is surjective. Otherwise, you might find minimizers, that you might find solutions that live outside your variational problem. And this is what happens. You find that using the Lagrange multiplier, there is a necessary condition for minimality that is in fact two different conditions. And the two conditions are, if the UEX is subjective, then there is a point, lambda, there is a covector in the cotangent space such that this equation holds, so such that the differential of J is equal to lambda the UEX. And then you can do the standard thing. You have an Hamiltonian, you have a nice description for the geodesics. This is the normal case. But if this thing is not surjective, and this happens, then you can find non-zero lambdas such that this lambda of the UEX is 0. And this is what's called an abnormal case. And the horrible thing is that what I was telling you before, you have multiple controls that that allows you to connect to points. It might well be that for one control, you are in the case of abnormal, and for another one, you are in the case of normal. So it might be that you have two different descriptions for a curve in this case that minimizes, that you can prove that those are minimizers, local minimizers. So, but you have two different descriptions. This you need to check with extra effort, but this you can prove they are minimizers. So there are curves that are both normal and abnormal that satisfy both this constraint, this problem, and this other one. And for the normal, everything is nice. You use Lagrange multipliers in the same way you do in mechanics. You have a solution in the cotangent space that is uniquely defined by the covector that projects you to a locally length minimizing curve on the manifold. And you have a nice Hamiltonian. And this is a really standard Hamiltonian. It's just the same form of a standard Hamiltonian, the same everything, but there's a smaller dimension here. So you don't have the p square half with all the p's, you will have only some of them. Here you see this, the structure of the distribution entering really into the Hamiltonian. And indeed, this is the degenerate on the fiber. So it's not full rank, it's not dimension n. And just to make you comfortable for the Dido problem, this is just p1 square plus p2 square. But you're missing the p3 square. It means that no matter which momentum you choose for z, this thing will describe the same geodesic. It does not see the p3. So for each point here, you will have many multiple choices that will project them to your curve down. And for the Grushin example before, you see that non-equiregularity creates issues at 0. 0 was the point in which Grushin was going from x dy to 0 and then back to x dy. And here you see that this creates issues. You can understand that this means that if there are length minimizing curves, they have to become flat when they get close to the singularity because they can't go in the y direction. But what I want to say is that Hamiltonian mechanics, as you know it, modulo degeneracies holds in this case. And so curves are smooth, they are local minimizer, and they are uniquely determined by an initial covector. Life is not that nice with abnormals. So the abnormals are those curves such that for non-zero covectors, this is 0. In the Riemannian case, your endpoint map is always subjective. There cannot be abnormals. In the contact case, it's the same. There cannot be abnormals. However, there exist abnormals. And before going there is a big question. There is a theorem called the Sard theorem that tells you that if you have a function of a certain regularity between manifolds, if the regularity is larger than a certain value, then the size of the set of critical value, so its image inside the target space, as measured, Lebesgue measured 0. So even though there might be a lot of critical points in your starting manifold, the image of those critical points, when you look at the target space, this might be microscopic. 0, well, with respect to Lebesgue. So it might be a huge set, but that's measured 0. So how big is the set of critical points for a sub-Riemannian structure? Is it 0 measure? Does it have empty interior, like in the Riemannian case where things are known? This is mostly open. There are a few papers that confirm that there's empty interior. There are some that says that in certain cases are 0 measure. A recent paper by Bellotto, Figalli, Barusniski, and Rifford that treats the step 2 and Carnot group, I think, if I remember correctly. But it's mostly open, nobody knows. This is one of the big open questions with the, alongside with the regularity of the small bolts. If you can say something about this, this is a really big open question. And to go back, there are abnormals. They can be very simple. If you take the Martinet, the one with the y square, the one in which your distribution, you need to take twice the brackets to be able to recover the third dimension. Then you find, it's weird, I know, that the lines passing to a fixed z, here you could put z0. And leaving on the plane y equals 0, those are all abnormal extremal, and they are length minimizer. And depending on the metric G that you choose, they might be normal or might not. So there is a paper by Agrachev and another by Baudouin and somebody else, in which they show that depending on the shape of this metric is either abnormal, strictly, so not normal, or it's both the solution of the Hamiltonian problem and an abnormal. The only thing is that is clear is that the fact that this is a minimizer does not depend on the metric you put there. Only if it's normal and abnormal, or only abnormal depends on the metric. And so this one is a topological minimizer in that sense. And all the example we know of abnormals, as far as I'm aware, but I've looked it up everywhere. Everywhere I was seeing the same. All the minimizers are all topological minimizers. All the known ones, and there's only some examples are known. Like there are for quasi-contact, there are for angles, and there is another example by, I don't remember the name, but it'll come back in a second. Those are all topological minimizer, NC1 isolated among horizontal curves. It's not known if this is true in general. That's completely open. And there are really finite number of examples. And so the other question is, are all the sub-Riemannian minimizers smooth? We know that all the normal minimizers are smooth. We know that all the abnormal minimizers that we have found until now and that are smooth are minimizers. So they're not just extremal, but minimizers. We know some non-smooth abnormals, but it turns out that of a few of them, you can prove that they are not minimizers. So it's not known if all the minimizers, normal and abnormals, are actually smooth. There is lots of work going on here. Very little has been done. And those works are from very different perspectives. Some are very geometric, some are very measure theoretic, some are very control theory oriented. So there is lots of ground for exploration and very little known still. And here there are a few of the readings and some other open problems on this question that I will not mention in this paper by Agrachov that is called Some Open Problems in Sub-Riemannian geometry. And yeah, this is the end of the first part. So